got some news. I don't put this news up before we do mindfulness. I didn't want your heads filled with this garbage. But now I do. Now I'd like to fill your heads with all sorts of crap. So, there's a new web work that I have edited multiple times, each time trimming more and more from it. So I tried to make sure there was no like repetitiveness in it and just some essential problems. This is going to be due next, when do I have here? I don't quite know when it's due. I think we should shoot for next Tuesday. That seems completely reasonable. Probably Monday, sorry, I think it's due Monday, which makes sense. I forgot we had Friday's class. Also, remember how we talked about taking a day off? You weren't here for that, but you probably saw the discussion in the thing. So we were talking about like Halloween or something like that, right? Like a Monday, taking a mental health day. To do this, we would have to like have our exam before then. And so I've been like, I spent a long time just like trying to figure this out. Like what can we do that's reasonable and not, not gonna stress anybody out, and still actually be meaningful. Those are the things I was like weighing. And I think that having it next Friday with a part of it being a take home would be pretty good. So like in class, we would have a very small, because I know anybody have class like right after this at 3? Does anybody? You do, you have a 3 o'clock?
I have 3:30 actually.
Okay, that's cool, that's good. That's actually okay, because that would almost be like normal, right? Like kind of our normal thing. But like Friday's exam would just be like simple problems, nothing challenging, just like to make sure that you're like actually learning along the way. Does this sound okay? And then like on Wednesday, I'll give you a take-home part and we'll start in class on it so that I can consult with you and it won't be, I'm not gonna try to brutalize you, but like some of these problems, I feel like you need to have time to think about and you'll learn more if you actually have that. So a little bit of a hybrid exam, and then we'll take Monday off. Yeah? Okay, all right.
What are the actual dates of these
The dates,
Next Wednesday is the second.
so next one is is what?
No, I think it's the second.
Next
What-
Wednesday is the 26th.
Oh yeah, you're thinking a couple weeks ahead. You're already past Halloween.
Yeah.
Friday's
Yeah,
the
yeah.
28th.
So what was the, next Wednesday's the 20 what?
26th, and
Okay.
Friday's the 28th.
Okay, so 26th and 28th, Lou.
Okay,
Does that sound okay?
yeah.
Okay, cool.
So the 26th is like the in-class exam, and then the 25th, take-home is due.
Yeah, so it'll probably be like, it might even just be some like a few web work problems and then like a couple written things that you write up and hand in on Friday. Like I promise I'm not gonna make this too crazy. Is this okay? Are you two like discussing this? Okay, awesome. That is why I was checking to see if you're gonna be here, Fernanda.
No, yeah.
Okay, awesome. So, all right, let's do this. So exam 2 is gonna be next week. See why I didn't tell you this before mindfulness, right? Like this is like, you're sitting there calculating all this shit out in your head. Next 2 weeks, so Wednesday, we'll have a take-home work in class part, and you will be able to consult with me on that, and I will help you. Like I'll answer questions, and I would ask, not work together on it, but you can ask me all the questions you want. Thursdays are my office hours, so you'll have time to like touch base with me on Thursday if you need to, and then that'll be due start of class on Friday. It'll just be a few problems. And then Friday, just a very small in-class exam, few problems. So, you can, like, I guess in some sense, I don't care if you even work with each other on this take-home part. I just want you to make sure you're ready for this. That's the key thing. So like doing it yourself and consulting with me is probably the best plan so that you're ready for this. This will be super simple problems. One would be like, here's a region, set up the integrals. Not surprising, that's gonna be in there. A couple integrals with infinity on them, not crazy ones, no like integration by parts and stuff like that. And then some differential equations. And this take-home part's not gonna be crazy. It's not gonna be like you have to block off Wednesday through Friday, okay? I promise you. I hope you trust me, because I'm here for you, and I want you all to be sane and happy, but I also we have to move along. So we can't just stay here forever frozen in time doing this stuff over and over again. And if we're gonna take off Monday, you know, we gotta pay a little bit ahead. So I will be getting materials ready in the next couple days and getting stuff to you. Maybe I can even get it to you before Wednesday. We'll see. I'll work on that. I want to give you the most time possible. Alrighty, so everybody cool on what's on our plate for the next week and a half? Yeah. Okay, great. Let's go back to differential equations. I hate talking about this stuff. It's always like, oh, we gotta have the difficult conversation. Now we'll have some fun. Well, we were talking about differential equations. There are a couple of apps up in a world-class announcement that are gonna be useful for doing some of this web work. This web work, some of these problems are like, you're just gonna be done with them instantaneously, especially if you understand what's going on. You'll look at it and go, oh, it's 5, 2, 3. And I'm gonna show you with something like this. So, let's say we have a differential equation that looks like this. And I've got some initial condition, but I don't want to talk about that yet. Plus some initial condition. But what I really want to do is understand what this is describing first. What does this represent? What does that mean, x dot?
Like x prime?
It's like prime, right? It's like a derivative. What is the independent variable here? When I use dot, so when we use prime, it's like dx. What's the
dt?
dt, yeah, exactly. So when you see this, you can rewrite that as dx dt. Did we start recording?
Yeah.
Okay, cool, thanks. Yeah, geez, it seems like a lifetime ago. So I've got this derivative of this function x with respect to time. So let's talk about what this is. The solution, or a solution is a function x of t whose derivative dx dt can be found by just taking the function, the expression, the formula for the function, and multiplying it by itself minus 1 by itself plus 2, whose derivative can be found by computing. So there's a secret x of t here. There's an of t that I'm not really writing. Can you imagine if I gave you this problem? I'd have to be a real bastard. Because to give you this problem, say, hey, just find me a function who you can compute the derivative of it by just subtracting 1, adding 2 to it, and then multiplying those together times the original formula. Like this, our brains don't work this way. My brain doesn't work this way. I have no idea what x is. This seems really mysterious. But what I can do is get a qualitative sense of what's going on. So what we can do is the following. We can notice some things about this. So I'm going to look in the plane. Here's my t-axis and here's my x-axis. That is telling me slope information. So again, remember, this is, and we started with this last time, this is the tangent slope to a solution curve. And, or a formula to the function that might solve this. And this tells me how to compute the tangent. Notice that the slope of the tangent curve only depends on the x-coordinate. So this is only need the x-coordinate. And be careful, because here the x-coordinate is like the vertical one. You're used to that being the horizontal, like x and y, but here x is the vertical. So let me put that here, vertical coordinate. So if I were to ask you, what is the tangent slope? So if the curve passed through the point 0, 1. So here we have t equals 0, x equals 1. What's the slope of the tangent there? You can use that formula to tell me. When x equals 1, what is the right side of the equation equal? 0, right? When x equals 1, this is 0, so we've got 0 on this side. So the slope, dx dt, so let's put this here, dx dt equals 0. Just using the right side of that formula. What does a 0 slope look like? Yeah, right? Like some Egyptian thing like that, right? So I'm going to, I'm sure the Egyptians would be like, we never did that. We literally never did that. So here, the slope is 0, so it's actually a horizontal slope. So I'm going to put a little arrow moving with time, because time flows in that direction. We can thank Newton for that nonsense, but that's what we do. Time is flowing that way, so that's how the curve would move that way. Can you see that if any time x equals 1, the slope is going to be 0? So for example, out here at -1, 1. Here I still have x equals 1. So the tangent slope is 0 still. Anytime the x-coordinate is 1, the tangent slope is 0. So actually, all along this line, x equals 1, I have a 0 slope. So here, dx dt equals 0 when the x-coordinate equals 1. And I'm thinking about this whole plane being filled with little arrows telling me where to go when I'm at a certain point. And there's the instructions for where to travel right over there. What's another x-coordinate where the slope is 0? At -2. Yeah, exactly. So when x equals -2, I got the same thing. So I'm going to come down here, and I got -1, and then -2, and this all along this line, dx dt is equal to 0 when x equals -2. So all along here, I'm going to put these little trajectories. These are telling me how, if I'm a particle and that's the equation of my motion, this is my motion. This is showing the flow of my life from -infinity time to +infinity time. Is there any other location? 0. So notice also when x equals 0, the right side is 0. So all along this x-axis, so here again, dx dt equals 0 when x equals 0. So that, what I'm saying then is if this thing is governing the motion of a particle, and that particle ever is on one of these lines, it never leaves these lines. If you're here and your slope is 0, the trajectory says go straight to the right, you go to the right. Your trajectory is still moving you to the right. These are all equilibrium solutions because once you're on them, you never leave them. So let's make a little note here. I have equilibrium solutions when x equals -2, 0, or 1. Because that makes, and let's write that here so that we have this in our notes, because at any location with these x coordinates, dx dt is 0. There's no change. There's no change in x at all in those situations. So I'm imagining this thing is a flow. There's currents flowing across the plane. And I drop a little leaf on it. And I'm interested in what the leaf does. So imagine this is like a table like this, maybe like some kind of infinite air hockey table. And it's got flowing currents on it. So I take the puck and I set it down and I watch what happens. And if I set the puck here, the currents just take it to the right, so I just watch it travel. Ooh, just cruising on that way. I set it here, it just cruises. Any of these lines. Now the question is, what happens in between? What happens if I drop the leaf or the puck on one of these spots? And so what we would have to do is go through here and figure out what the arrows look like in these different locations. Let's actually just do one, for example. What about if x is equal to, let's see, what is that? That's 1. What if x equals 2? What is dx dt when x equals 2? 8? Yeah, really intense. Does everybody see where that's coming from? When x equals 2, this right side is valued at 8. So all along x equals 2, the slope is 8. And I mean, it's really hard to draw that without it looking vertical. What is the slope when x equals 1/2? Sorry, you gotta do fractions. Really, folks lose their minds. Normally sane folks lose their minds when fractions come up. So when x equals 1/2, what do we got? 1/2. So x dot equals 1/2 times -1/2 times 5/2. It's 2.5, right? And so that's -5/8. It's not too bad. It's a little steeper than a -1/2 slope. So right along here, on x equals 1/2, here I've got dx dt equals -5/8. And that looks kind of like that. What about at x equals -1? What is happening here? What is my slope? Is it 2? I didn't even try. I'm going to take your word for it. X equals -1. Yeah, that looks solid, right? So does everybody agree we got 2 coming out of the right-hand side? All right, so that's pretty steep, but it's not that steep. So we'll pretend that's 2. So here, x dot is equal to 2, and this is at x equals -1. So I've got little arrows like this. And then we got one more region we really need to check. We know that it can't be 0 anywhere other than at 0, 1, or -2, so I don't have to worry about the sign changing. Once it's positive in here, it can't change sign until you cross the 0. Right? To change sign on something, you have to cross 0 if you're continuous. And we're all continuous here. Let's do one last one. How about at -3? So when x equals -3, what is my slope? It's going to be, I think, not too insane. Or actually semi-insane. Is it 12? I think so too. It looks like a positive, yeah, it's positive 12. So here, slope, and I'm going to use m to be a little suggestive, not like, you know, like I have a low-cut shirt on or anything like that, but like suggestive of what this stands for, its slope. So here we have m equals 12, and that's steeper than that 8 up there. Good Lord. But we'll just show it's up, and it's pretty damn steep. So we're starting to get a sense of if I drop a leaf on this table, or a hockey puck, what would happen to it? So here, I get a sense that if I dropped it like right here, it's going to move up this way. Would it surprise you that the slope becomes closer to 0 as we move up this way? That doesn't sound, right? Like it's not gonna move from what are we at here? Do I do this, have I done this before? Yeah, thanks. Everyone's just like, yep, yes you have. That to get from, what did I say this was? What was the slope here? I'm sorry. This was at 2. Oh, it was 2. Yeah, to get from 2 to 0, you have to kind of decrease. So the next place, the slope is kind of getting less and less. And I can't really ever enter that stream right there. If I started up here, I would maybe go like this, down to here. And if I got close to this, I'd have to be negative and flow down this way. If I got a little bit above this, it's probably slightly positive. And then as I move up, it becomes more and more positive, like that. And then this one is like, if I came this way, it would kind of go like that. And then down here, we would have behavior where it rockets me up toward this one, and then the arrows become closer to 0 in slope. So I could fill the whole plane with this sense of what things do. So look at this, I haven't even solved anything. All I've done is look at that equation, what does it tell me about slopes, and then fill the plane with arrows and get a sense. So let me show you the tool I want you to use for some of your web work. Please didn't log, oh good, didn't log me out, okay. Thank you. Outstanding. So in the announcements on World Class, I provided links to a couple of tools that will help you in just messing with this stuff, understanding it. It might be quite useful for whatever take-home part we have last. Boy, that is, okay, we're not cut off there. You know, I'm gonna kill the lights completely, so, because it's a little dim. Awesome. So check out this little box up here. See, it says dy dt equals, and then I can enter the equation on the right side. Now, we had dx dt, but this is, just replace the x with a y. It's got the same information. Instead of x, they're using y up here. So let me show you what we would do for the equation we just had. I would enter x. This is all getting recorded too if you ever need to see it again. Times, and I use the asterisk for times, x minus 1 in parentheses times x plus 2 in parentheses. Now watch what happens when I hit enter. Nothing, because I have to click this button. Okay. So it has actually done the work of filling the plane with these arrows, but they're not really great yet. I'm gonna click this button to variable length. Maybe this isn't the app we want to use. I'll show you the other one too. What the hell? Boy, that looks weird. That looks really weird. Did I type that thing in right? Oh God, it's Y. Just like I said, no wonder that looks so messed up. Sorry. So y times y plus 1 times y, or y minus 1 times y plus 2. That's why that looks so terrible. Now I click the button because I learn things. I can't see things, but there we go. Okay. Now can I blow that up a little bit so that, okay, yeah, that's definitely helpful. Let's get a little bit bigger. That's nice. Okay. So it has done the work of going to every single, not every single point, but a lattice of points in the plane and putting the slope information in there. So now what I can do, and I can click on here, and it shows me what the solutions would do. Look at this one right here. So I'm at right above 1 right now, and notice how those are shooting up, like this one here, right above 1. Let me click one right on 1, if I can even, look at that. I clicked on 1, and it keeps cruising across. Let's click on something right below 1. Oh my God, it's almost like I understand things. Almost. When I click on 0, well, that's hard to get. Oh man. Okay, they're kind of on it. But when I click below 0, does that look like my curves there? Yes, it does. And when I click right on -2, I get that. So I can kind of click through the whole plane and get this one. I must have screwed up something down here.
I think it's supposed to be -12.
-12, thank you. That makes much more sense. Thanks, Cassie. So this should have been -12. Video, folks. These arrows should be pointing down this way so that our solution's actually like this. Okay, let's talk. So first off, that's beautiful. I just freaking love that. But let's talk about what's going on here. If this represents some kind of a physical system, these are my equilibria right here at 1, 0, and -2. What happens if the hockey puck is cruising on this equilibrium, or the leaf? I like the leaf better. I'm not a sporty guy. I'm more of a like fall into a pile of leaves and kind of guy. That's the kind of guy I am. Lay in the autumn leaves guy. So I've got a leaf on here. If it gets blown off this trajectory in either direction, what happens to it long term? Goes away from this equilibrium, right? So this is an unstable equilibrium. Remember when I was balancing the pens? This is the pen balancing. Any slight perturbation, left or right, sends things careening away from the equilibrium. What do you think we might call this one right here? Stable. Yeah. If you veer off of this to either side just a little bit, you will come back to it. And then what about at x = 1? What kind of equilibrium? Unstable. So right off the bat, without doing really much math, like simple arithmetic, we multiplied some numbers together and plugged them in, we understand a very complex system holistically. So this is called a qualitative understanding of things, because I understand the quality of the solutions. I understand stability from this picture. We can do lots of things with this picture. So for example, we can study all sorts of complicated things that would just be very painful to study otherwise. What if I had in here sine of y? So that's, why do you say that? Why do you say that? I love the way you're thinking. So let's talk about this before we see the grand reveal. Let's talk about it. So if I had, here's my eraser. Right there? Okay. Conversations with myself. So I've got this dialogue going on in my head. Tonight is my game night. with my friends. I think I've met, like Wednesdays and Sunday nights, we get together and we play Elden Ring, one of the Soul series. And I wore my, and today, this is my Dark Souls shirt. If anybody knows Dark Souls, this is, Praise the Sun. One of the things that makes me and my friends laugh hysterically is to call each other fucking idiots. It's just, for some reason, is the best thing in the world. You fucking idiot. And then we all laugh. I don't know why, it's stupid. But I was just calling myself that in the head, you fucking idiot. And laughing in my head. So.
Wait, Dr. T, what is this website called?
Oh, and the link is up. Look, if you can get into World Class, Josh, look in the announcements. I honestly don't know. It's called aebo19.hostedruark.edu/ go to the link. It's the second one. That one's like GeoGebra. It's the second one. Make sure, is that showing up? Let me know.
It is.
Okay, awesome, thanks. Cool. So, yeah, so let's take a look at this problem. So we've got y dot equals sine of y. Don't have any initial conditions because we're looking for a very complete understanding of this. So Olivia, what is the slope at an equilibrium solution? Zero, beautiful. When this is zero, we have equilibrium because there's no change. That's what equilibrium means, a state of no change at all forever. So we have equilibrium. And I know you'll love to have a conversation with me. Yeah, so just thinking about sine of y, and so Olivia was asking, sine of y, wouldn't that go like this? And it would. But we're not looking at it in the same way now. We're looking at it as the predictor of our slopes. Does that make sense? Yeah. So when does sine equal 0? We never had that quiz with that graph. We won't. Give me one place where sine equals 0. At pi, 0, 2 pi, any multiple of pi, right? So for this system, we get when y equals a multiple of pi, we've got an equilibrium solution. Now look, what's my independent variable here? It's not y, it's t. So I have t here, I have a y here, and whenever y is equal to 0, I've got an equilibrium solution. So it's 0, ooh, that's pretty crazy. At pi, at 2 pi, that one got really intense. It's okay. At negative pi, how many total equilibrium do I have? How many zeros does sine have? 5? Is this it? Infinitely many, right? So there's infinitely many equilibrium here. Between 0 and pi, is sine positive or negative? There's sine of y, there's y, here's sine, right? There's pi. So between 0 and pi, should I have positive slope or negative slope?
Do you have to break it down even smaller?
So explain to me what you're thinking, Kidra.
Like, my immediate thought was like pi over 2 for between 0 and pi.
Yeah.
But
Yeah.
then that gets you,
Like right there?
yeah,
Yeah, what's that slope?
just the 1.
It's 1, right? So we could, but we also know, are the slopes positive or negative in there? You're right, like if we were really getting a good detailed one, I would absolutely want to do that. But between 0 and pi, what is sine of y in terms of positive or negative? Positive, right? It's all positive in there. So in here, and I guess I'm just trying to I'm doing something a little less refined than what you're thinking, Kitra. But I'll do it, that's like pi over 2, about a slope of 1, right? What about between pi and 2 pi? In this band, what is my slope? Negative. Sine of y is negative, and sine of y is my slope. So in here, slope is negative. And then it just keeps alternating, right? It just really alternates the whole way through. And I'm being super sloppy, but I'm not interested in precision here. I'm interested in the qualitative nature of things. So this fills the entire plane with these equilibria. Is this one stable or unstable? Stable, unstable, stable. So they're alternating back and forth. So we're going to see a bunch of solutions that look like this. And the equilibria always act as asymptotes. You can't really get into them. You can only approach them. Because you think about it, the arrows are getting closer and closer to zero slope, but never really getting there. So you got this like gradual descent, gradual ascent here. So let's see if I'm right. I'm right, but let's just verify. So let's click this button. And so we're getting a sense how that all works. And that goes on forever and ever. It's kind of got this beautiful pattern to it, beautiful rhythm to it. We're going to come back to this on Friday. And we're going to understand what on Friday, really important day, we're going to understand how this picture gets made. And it's a thing called Euler's method. And that's something that I'm going to have you, that's something you'll do at home. So you'll do an Euler's method for me by hand. And it'll be okay. You won't even need to graph, it's all like an algorithm. So I'll give you a nice algorithm to follow. But basically, here's what's happening. You start here, you find your slope, you follow that slope a little bit, recompute your new slope using your formula. Follow that a little bit. Recompute the slope using your current your formula. Keep following that. So you just keep checking. Move a little bit in the direction you're told to go. Check to see what the new direction is. Follow that direction. And just keep using the formula over and over again. And that's what this thing is doing just on a really fine scale. Like it's just taking tiny steps, so small that you get this beautiful flow like this. So, the other app, let me show you the other one that you can use. It's really a matter of preference. So the way you can find these is you just type slope field calculator. You'll get a bunch of things up. So the Desmos one sucks. But this one, this GeoGebra one, this one's nice. Look at that. See, that's very pretty. So here, they're using X and Y instead of Y and T, or X and T. So here, X is the independent variable. Like right here, I could type sine of Y, and that would give me the same picture. I guess I have to hit enter for this one. See, there we go. And then what I don't like about this one is I can't choose where I get to see my solutions. I love the other one because you just click on the graph and then a line shoots out of it. I think that's really cool. This one's got some predefined crap, which is, man, yay. We'll come back to that. But now you have something to entertain yourself with between now and Friday and for the rest of your lives. Slope field generators, they're so freaking awesome. All right, let's get back. We're gonna do some quantitative stuff for the last half hour. And this is down to earth. You know this is just gonna be Calc 1. And maybe a Calc 2 in there once in a while, but mostly Calc 1. So how do we actually get a formula solution? We're not gonna do that. I did this before class just for recreation. I was like, oh, I wonder what X of t would look like, and we're not gonna do it. But we're gonna do some simpler things. It was quite beautiful and cool. So, how to get an explicit solution to a differential equation. I mostly wanted to spend the first, 45 minutes talking about what these things actually represent. They're flows in the plane. And the solutions are curves that obey those flows. But maybe I want a formula because maybe I'm Newton and I'm trying to find a law for cooling, and I want a formula as opposed to a differential equation to give people. Because I want them to be able to just crank here. What will be the temperature at this point? Just plug it in and chug out. So we will only focus on a very specific band of equations. There's a course on this that I'm teaching in the spring, and there's a lot to learn. There's a whole course to learn, and then maybe a graduate study in just differential equations. So we're gonna take just the tiniest sliver, the wafer thin sliver. We will focus on what are called separable first order differential equations. These are equations of the form d some variable over d some other variable, and these are going to change all the time. It could be y and t, x and y, good lord. I got a couple today that got a g in there or something. Is equal to some function purely of this top variable times some function purely of this bottom variable. So these are pure functions multiplied together in a product. And I'm going to give you an example. This might be a little abstract right now, but we'll also have an initial condition with an initial condition that goes something like, shit, I'm not going to write out all that stuff. With an initial condition, we'll just leave it there. I'll show you how to use that. We get a little too abstract. So what do I mean? Example. dy dx equals x times y. There's a nice product, right? So this would be one of the, I've got a pure x function times a pure y function. Our method of solution. Step one, separate the variables. Hence the separable part. And so this is going to happen by dividing or multiplying. It's going to be pretty straightforward. But you basically, if you've got a dy, you want to get all the y stuff with dy, and you want to get the dx with the x stuff. Separate the variables. So, e.g., all x stuff gets moved to dx, all y stuff, and I'm just talking about this one here, and you'll get the flow of this after we just do a few, gets moved to dy. So like this thing over here, and I can illustrate this here. We're gonna treat this d thing, this d over d thing, like a fraction, like you're always told not to do. Like, right, when we first learned calculus, like, this is not a fraction, this is notation. Well, now it's a fraction again. And that's fun. Because what I'm gonna do, if I was gonna separate this, I would want to get all the triangle stuff with d triangle. And you always want the d things to be on top of any fraction. You never want this to be underneath something, because we're going to integrate them in it. So this one here, if I was separating it, I would bring this f underneath, and I would multiply both sides by this. This isn't a general formula, because sometimes it's just going to be weird, but I'm showing you what I mean by separating things. So yeah, don't count on this as the way things will always look, but kind of. So over here, I want to separate. Let's get an initial condition. Y at 1 is equal to 2. So this is my initial condition. But let's do the separate part first. So for this thing, I always want the D, make a little note here. D stuff, D whatever, always goes on top. So, I knew that was too many L's. Always goes on top. So, I'm going to leave that dy up there, and I'm going to divide both sides by y, and I'm going to multiply through by the dx. That's what I mean by separating. And the operations you need are going to vary from time to time, but it's always going to be multiplication or division. Step 2, integrate each side. That's what we've been talking about, right? So you know that had to come in. So I'm going to just write an integral on the left and an integral on the right. And I'm going to do those integrals. What's the integral on the left?
Is it natural log of y?
It sure is, natural log of y. Let's pop some absolute values on there for the safety's sake. Little guardrails, right? Being safe. What's the right side?
1/2 x squared.
Oh, thank you. Okay, I'm glad we know that. And then yield plus c. So I would always put the plus c on the independent variable side. So add plus c to the independent variable side. An independent variable is the thing that's under the derivative. So like here it's x. There's a solution. It's not super satisfying because I wish it was y equals something. So how do I do that? So I'm going to take my shoes off. I'm going to take these off. Just knock everybody out if somebody doesn't tell me how to do this. How do I do this? How do I undo a log? If I have natural log of the old triangle square thing equals that, what's another way to rewrite that? Well, I'll tell you. So this is equivalent to e to the triangle equals the square. Or square, how about the square equals e to the triangle. So now you got a little formula, right? So this actually translates to, this is in the square, this is in the triangle. I don't want to be super goofy, but it doesn't hurt. So this is absolute value of y equals e to the 1/2 x squared plus c. That plus c is now part of the exponent. The whole side is that triangle, so that all comes up there. Does that make sense, Kitra?
Yeah.
Yeah. You can probably get rid of these at this point. Now everything's safe. Okay. You're gonna love what happens next. And it's probably something you've never seen before if you haven't had differential equations, and I hope you haven't, because this class is a prereq. And that probably was a disaster. So maybe that's why you're here. You're in differential equations, you're like, oh my God, I should not be in this class. I need to go take the prereq. I had that happen. I'm teaching abstract algebra this semester, and I had a gentleman show up on second day. He just kind of walked in. I was like, oh, hi. He's like, hey, I'm in your class now. Okay, cool. I didn't see you join. And he sat through the whole class, and at the end of it, he came up and said, "There's a prereq for this class, isn't there?" And I was like, yeah, there's a bunch of prereqs for this class. So like abstract algebra is one of the highest level math classes we have here. You have to know how to prove things. And that's all we do in there is prove things. And he was and it was like, he's a cool guy. And he knew, what I appreciated is he knew what he knew and didn't know. Man, like if you know what you don't know, that's a good thing to know have in life. So let's take that, we've got y, I'm just gonna rewrite it. And you're gonna see this trick often. This is actually the multiplication of those two things. Does that make sense? Because I would add the exponents, right? Common base. So I'm doing that. The great thing about the constant in differential equations is it just eats everything and just keeps becoming c. So I'm just gonna call that c again. We'll figure it out later. It's all good. So this is just, I'm gonna move it in front, c e to the 1/2 x squared, because I like having my constants in front. This is a constant. Just make a little note. Just a constant. So I pull it out in front. Now I know what every solution looks like. It looks like this. Let me prove that this, and I haven't done the particular, so this is the general solution. We don't know what c is, but this for any c works in that equation. I'm going to prove it to you. Here's a check. Check to see that it's a solution. I'm going to take its derivative. I'm going to find dy dx. And that's just the derivative of the right-hand side. Derivative of the exponent. When I take e, right? I'll just remind you of some things from the past. And to take the derivative of e to something is just e times the derivative of the exponent. So this is times d dx, 1/2 x squared. And I'm going to simplify that c e to the 1/2 x squared times x. I'm going to erase this reminder here because I need the space. Notice that this is actually just y again, isn't it? That's what I said y was. So look, this is just y. And that's that exclamation, that's not factorial, that's excitement. This is dy dx equals y times x. That's the equation. Cool, this worked out. Vivian, can we explain that a little bit more? Just furrowed brow, I'm noticing. What part would you like to talk about?
I lost you for my check.
Okay, cool, awesome, let's go through it again. So were you okay with this?
Yeah, yeah.
Awesome, awesome. So I took the derivative of each side with respect to x. That's, yeah, you're all better now. Wonderful. I'm sorry, I didn't say that right up front because I don't think I exactly said that. Ooh, shit. We still have this. So now is when you figure out what c is. So this is like, let's see, God, did I have stuff? So step one, maybe I would say step 3 is solve for y. Solve for the dependent variable in terms of the independent. Not always needed, but it's something I'd like us to do. It's what I would do. And it works better on our brains. Our brains aren't good with, like, when you see an equation like log of y equals that, your brain doesn't process. But when I see this, I'm like, oh, it's just e to a power. It's like, you know, something like that. I can understand that. So then step 4 is use your initial condition to find c. That's it. So, y equals c e to the 1/2 x squared is our general solution. Works no matter what c is. We want the curve in the plane that goes right through the point 1, 2. Right now, we're looking for that exact curve. The one that goes, because otherwise, you know, there's all sorts of curves in here. So just plug in the values. When x equals 1, y equals 2. That's what that says up there. So I'm going to plug those in. And I've got 2 equals c times e to the 1/2 times 1 squared. And so 2 equals c times e to the 1/2. And solve for c. C is equal to 2 e to the negative 1/2 power. Or, you know, 2 over e to the 1/2, if you like. I just divided both sides by e to the 1/2. That's all I did. So that's c. And then rewrite the solution. Lastly, rewrite with c value fixed. So my final solution is y equals 2e to the negative 1/2 e to the 1/2 x squared. And that solves my differential equation. It ain't pretty. I just made it up on the spot. I thought it might be a little nicer than that, but that's it. Good Lord. Sometimes our days in here are quite the trek, aren't they? It just feels like, wow, we're like hiking up a 14er. Let me give you one that's less intense. Your turn. dy dx equals, let me make sure it's easier. Yes, this one will be easier. X over y. And x times y, now we got x over y. Let's go through this together. First, separate things. For this one, you just multiply both sides by y and multiply by dx on both sides. Does that make sense? Separation? Cool. Now just integrate each side. It's just old power rules. So step 2, integrate. I didn't give an initial condition, I guess, did I? No. So, what about y at 0 equals 1? And that means when x equals 0, y equals 1. Let's find out that exact solution. But when you integrate, you should get 1/2 y squared equals 1/2 x squared plus c. Are we getting this? Yeah, awesome, solid. You're solving differential equations. Look at that. Hell yeah. If you want to solve for y, that would be nice. Don't forget c will eat anything, so if you multiply through here by 2, you can just rewrite it like that. Check this out what I did here. I multiplied through by 2 to get rid of the 1/2 because I just wanted to get that y by itself. So the C just ate the 2 up. So it would have been 2C, but I'll just rewrite it as C. C absorbs everything. So instead of this, which would be the natural thing, multiply both sides by 2, just call it C again. It's all good. What do I have to do to solve for y here? Square root, yeah. Let's talk about that, because you can just go ahead and do square root, but you gotta be careful. When you are the one square rooting, you need to be careful. You better be putting a plus or minus in there. Now, there's 2 possible solutions. Notice that our y is the positive one. So we're gonna make a choice here. So let me actually write this all out. Since our y equals 1, which is positive, we're gonna choose the positive branch. So we have y equals just good old, just what you probably did anyway, without what you would have done if you hadn't thought about it like super from the base. And then we just have to find C, and I think, yeah. So I guess that's, I don't know, is that my step 3 maybe? Yeah. Step 4. X equals 0, y equals 1. So I get 1 equals square root 0 squared plus c. So I get 1 equals square root of c. What do we think c is? 1. Square both sides. Plug it back in. So now we're down to rewrite. We got y equals square root of x squared plus 1. And that, if you sketch that out, you would find, looks like this. Let's see, 0, 0, 1. There's my initial condition. Actually, it gets kind of asymptotic to the diagonal. Differential equations, solving them, doing math. Oh Lord, I'm completely exhausted. You might be too. Say we call that a day. I'm certainly not going to start a new problem now, because it just would be cruel for all of us. My voice is shot. See you on Friday, my friends. Did you? Thank you, sir.